Our next topic is integration via software. The purpose of this section is to help you do the various integration and other calculus methods needed for this particular class. What I have found through teaching this course is that one of the most difficult aspects of the course for the students is how to do a particular kind of integral. In terms of, let's say, using the U substitution method or using integration by parts. For whatever reason, students struggle applying what they've learned in a calculus course. Now, the purpose of this course is not to reteach calculus, rather is to apply what was learned previously. And so to help students out then, I'm going to introduce to you two different methods where you could use software packages to essentially do the integration for you so that you don't have to do, let's say, integration by parts using by hand calculations that you would learn in a calculus course. So to help introduce then these methods using software, we're going to go back to this transaction time example that we saw before. So our random variable is x. Let me get my pen out. And our PDF here is, oops, let me get my red pen. Our PDF here is f of x. X has to be greater than or equal to 0. Here's a nice little plot of what f of x looks like. And the first way, or what we've done previously using calculus, is we found probabilities associated with this PDF, such as the probability that x is greater than 0. How do we find that? Well, we integrate from 30 to infinity of f of x dx. And in this particular case, we get 0.37. So again, what that means then is that from 30 all the way out to, if I could go all the way out to positive infinity, that area underneath that curve is approximately 0.37. Okay, let me erase that. Also, we've looked at finding probabilities for a particular interval, such as 25 to 100. Again, using calculus, using integration, we found that to be approximately 0.4. Now, to do this in R, we're going to use a function called integrate. And integrate uses a technique called adaptive quadrature to numerically find the result from the integration. And you don't need to know the details about how adaptive quadrature works, but I just want to briefly give a explanation of what's being done. Suppose here on this plot, I could draw some bars. And they're going to be, let's say, they have equal widths. And I can keep on going throughout the rest of the plot, where the main thing is that the middle of the bar at the top actually intersects with our line for our PDF. And if I wanted to, I could find the area of each of these bars using base times height. And because of how I drew then these bars to about the top or the height of the PDF that we see there, that red line, then the area of all these bars summed up then should approximate the area underneath this curve here. That's essentially what adaptive quadrature does. It could also, there's various ways to implement it. Another way would be not to necessarily use equal width bars and maybe use smaller width bars when that function is changing a lot, or using wider width bars when that function is not changing a lot. Okay, so now to implement adaptive quadrature in R, again, we're going to use a function called integrate. And this integrate function needs to know what you're trying to integrate. And to do that, one actually has to write your own function. And so we've seen how to write a function briefly in the past. Let's just review how to do this here. Let me actually jump on over to 10 to do this. Let me page down to where this is in my program. So I'm going to create a function called PDF, for the lack of a better name. It's going to get a function which has one argument in it called x, for the lack of a better name. And inside the function, which is the main body of the function is denoted by these curly brackets, this is where I put my f of x value, written in the context, or the syntax, I should say, of r. So 1 over 30 times the exp function minus x divided by 30. Now remember, whenever you write a function, the very last line of that function, when you run it, is what's returned to the user. So let me go ahead and run this small set of code here. Okay, so if I type PDF, I see the actual functions in R. And if I want to actually use the function, let's say PDF x equals 0, so I want to evaluate my f of x value at 0, I get 0.033. Well, why? Well, what R does, it says, okay, you want x to be 0, so wherever you see x, then inside this function, I'm going to put a 0. And since this is the very last line of the function, then 1 divided by 30 times e raised to the negative 0 divided by 30 power is returned to the user, and that's what we got. And in fact, I actually show here, well, what if we just evaluated it directly? One could run it with x equal 10. So in other words, you're just doing the height of the curve when x is equal to 10. Okay. Now that we have this function here, which represents our f of x, we can now use the integrate function. So I say integrate, first argument's f for the function that you want to integrate. I want to integrate PDF. And my lower bound is going to be 30. My upper bound is going to be positive infinity. And the R, let's say reserved word for that is a capital I and then an NF. And if I were to run this code, it gives me the probability that x is greater than 30, which we've calculated using by hand methods in the past. And guess what? I get approximately the same that I got previously. Now, with using the integrate function, this is a numerical integration method. So again, it's trying to approximate the necessary area underneath that curve. And so with that, as you might expect, it's not going to be perfect. There's going to be a little bit of error associated with it. And so we have some kind of measurement of errors here, and that is fairly small. So I'm fairly confident that this numerical integration is giving me an accurate result. If instead I saw this absolute error was, let's say, 0.1 or 0.01, something that's not as small as what we see right now, then I might worry about, okay, is this numerical integration work give me an accurate result, give me an accurate approximation? And in those situations, what you can do is ask R to be more precise. And the way that you can do that is to use the rel.toll argument. And you can put in a very, very, very small number here in this relative tolerance argument. And if I run that, we can see that I essentially got exactly the same thing as what I got before, but now R is more confident. It's giving me a smaller resulting error in the end with its result. To find the probability that x is between 25 and 100, again, we can use the integrate function. Now my lower argument is 25, my upper argument is 100, and again, we get a result which is very similar to what we've seen in the past. Let me get back over here to my notes. Okay. Another problem that we saw previously in the notes was when I needed to find the 0.95 quantile from this probability distribution. In other words, I want to find the value of C such that the probability that x is less than C is equal to 0.95. And when we did that then, we took the integral from 0 to c of f of x dx, set that equal to 0.95, and then solved for c. And we got approximately 90. Let's look at how we can do this now in R. So to help set this up, here with the integrate function, I'm going to again use my f as what we saw before, that PDF. And let's actually integrate from 0 all the way up to 89.87, what we know what the value of c is. And if I were to do that, and actually let me come over here to R to do this. And the reason why I'm doing that is I want to show you that in D we are getting what we would expect, a value of 0.95. And so if I were just to run this segment of code with integrate, I get approximately 0.95. This time though, how about we save the results into an object? And again, for the lack of a better name, let's call it save.res for results. And notice nothing comes back to my screen. And that's because all the results are saved in save.result. And there we go. Now, this save.res is what R is calls a particular, well, let me back up. Save.res is an object, but it's a particular kind of object called a list. And we've seen lists before in the context of a data frame. And if you remember, if we wanted to see components of that data frame in terms of the individual variables, what we would say is names and then the name of the data frame. Here with save.res, we can use names as well. And we see it has 5 different components to it. And if I want to see one of those particular components, such as value, I can say save.res $value, and what do you know? We get this integration result. If I did abs.error instead, we get this measurement of error that we had before. Okay. Let me come back here to Word. Now, the reason why I bring this up is this is going to help us with our calculations shortly. So again, I can say save.res $value, and I get the result back. Now, a little bit of a shortcut to get that result back and only get that result back is instead of saving the results of integrate into an object, I can immediately use integrate and then $value so that R will only return the result from this integration, the 0.95 approximately. Okay, let me make a little small change there. Okay, so here's why we want to do this. So now remember what our goal is going to be is we want to solve for C in this particular integration that we're doing here. Now equivalently, you can think of it this way. We want to solve for C in this particular equation that is set equal to 0. So 0.95 minus my integral is equal to 0. And you've seen this in algebra classes before, essentially, where you have one unknown and you want to solve for it in an equation that's equal to 0. In other words, you want to find the root of the equation. Okay. Now, based upon what we've done previously in R, if I take 0.95 minus then that result from integrate, I'm going to get a value that's close to 0 because the root of the equation is this 89.87. And so in R, there's a function called uniroot, which finds roots of the equation. And so what we need to give uniroot is a function that we want to work with that eventually we want the result from evaluating this function to be equal to 0. So let me come back over here to 10. And so what I'm going to do is write this function called find.root for the lack of a better name. It's going to be a function. It's going to have one argument called c.val. The reason why I'm using c.val there versus c is because, remember, in R there is a function called c. And in the end, I'm going to take 0.95 minus the results from my integrate function, where I'm only going to work with that value. So that if I were to run this function and then, put the function in R, then run it with a c.value of 89.87, as you might expect, then I'm going to get a value of approximately 0. So using this then, we're going to use the uniroot function to numerically find, or I should say iteratively find, what the actual value of c is without me telling what c is first. And so with uniroot, my f is my function that I want to be equal to 0, find that root. And then I need to tell R where to search for that root. So I'm going to search in an interval from 0 to 300. Why am I choosing that? Well, just from looking at the plot that we saw previously of the PDF, we realize that, well, that 0.95 quantile is somewhere probably between 0 and 300. So let me go ahead and run that. And this is what I get. So R finds this root of the equation, our c value, to be 89.87, which is what we had before. It actually evaluates then this function at this particular root value, and we get something that's very, very close to 0. Just to make sure that you understand this, and I know I've passed over this before, this value here represents 4.62 times 10 to the negative 11th power. This is just scientific notation. R took 9 iterations in this numerical method that it used to find the value of c. And this also then gives us a measurement of, well, how much error do you think exists in this actual end result? And we can see that, that this is very small. So we're confident that this indeed did work. It did find this root of this equation. Okay, so that's how you can use R to find numerical quantities associated with integration. It's a very, very useful tool, and we'll use it many times during the semester. Now, there are other times during the semester where we will want to actually symbolically evaluate an integral. So we don't want a numerical answer. We want, let's say, the actual mathematical symbols in the end associated with some quantity that we're trying to integrate. And in that particular case, it's not very easy to use R. There have been some methods developed, but I haven't been too impressed with them. And so because of that, what we're going to do is using mathematical software package that allows us to do symbolic integration, allows us to do symbolic differentiation as well. The package that I've chose for us to use is something called Sage Math. Most people just refer to it as Sage, so I'm going to just call it Sage here. Sage is a free open source software package for computer algebra, for doing calculus. Now, Sage is meant, so first of all, let me back up a second. So it's going to take a little bit of time for us to actually get into using Sage. There's going to be some information I need to tell you about it first so that we can actually use it. The first bit of information I need to tell you is that Sage was actually designed for Linux-based operating systems. However, if you have a Windows-based computer, that's okay. There are a number of different ways that you can use it still. As I mentioned before, Sage is available for free, just like R. You can go to its website and actually download it and install it on your computer. If you have a Windows-based computer, what Sage will actually do is install basically a Linux emulation software package onto your computer first, and then install Sage with it. I will tell you it is a pretty substantial download, and it's going to take up, I think, at least 1 gigabyte of space on your hard drive. So as an alternative to that, what I will focus on in this particular class is using a cloud computing way to use Sage, where essentially we can use Sage through a web browser. It's not perfect, but I think it will be good enough for our particular class. So to actually implement, and this is free, you can go to the website cocalc.com. This was actually created by the person who created Sage itself. And there are a number of different ways within cocalc.com that you can actually use Sage. All of them are web browser based, and we will focus on one way that uses what's called a Jupyter notebook. So again, there's a lot of information I need to give you in order to actually for you to get to using Sage. So please be patient. Okay, so let me actually go to cocalc.com. This is what the website looks like. You can use it for free. They do have options available to you to pay for it if you wanted to do that route. By paying for it, you get more storage space on their server. It will also allow you to have faster computations. For our class, I plan to just use simply the free version. But I do recommend that you actually get an account and sign. So you have to actually click on sign in to get an account, and that way you can actually store some of the programs or actually Jupyter notebooks that we are going to create. You can actually store it on their system. It will just make it a little bit easier for you, but you're not required to. And again, the account would be free. Now, if I don't have an account, how can I actually use Sage? Well, if you notice here, you don't see anything that says Sage. And again, the reason being is because we are actually going to use Sage through another software package called a Jupyter notebook. So I'm going to click on Jupyter. Without getting into all the details behind Jupyter, Jupyter is actually a large project that came about a number of years ago that allows people to interface with various programming languages, including R, including Python, and also software packages such as Sage. If I come down here and click on Run Jupyter Now, and eventually we'll get to where we need to be. I have to admit that there are some aspects of using CoCalc that I don't like, and that is it can be actually a little slow at times. And next one I need to do is select a kernel. In other words, how do I want to use the Jupyter notebook? Like what programming language, what software package do I want to use with it? And so if I come down here, you see Sage Math. So I click on that. And now we are in a Jupyter notebook that allows me to use Sage. Okay. Now, with a notebook style format, such as a Jupyter notebook here, you could say an input, and then there's always going to be an output. So if I simply type 2 plus 2 at this in box here, or what Jupyter will call a cell, and if I come up here to this, what looks like a right arrow there, and notice when I mouse over it, it says run cell. If I click on that, the first time that you run something, it's usually a little bit slow, and then eventually the calculation will come back to you in an out cell. There we go. The first time, again, it's often a little slow. And so 2 plus 2 is equal to 4. That's in my out cell. If I do something like this, x equals 2 plus 2, I can save the results of 2 plus 2 into a variable using their terminology. And if I just type that variable name again, it will come back to my screen. Again, 4. Let's say I do 2 plus x now. And if I click on the run button, Now it takes what was an x before, 4, and it adds 2 to it and gets 6. So you can do basic math. You can create variables in Sage as well. Now, if you've never worked with a notebook interface before with some kind of mathematical software package, there's one little aspect to it that I don't like and that I want to bring to your attention because it can actually cause problems for students if they're not aware of this. Now, I can actually go back up to one of these cells that I've done in the past and make a change to it. So it's very convenient. So now instead of 2 plus 2, let's say I want to do 2 plus 3 for x. Run it, and notice I get a value of 5, of course. Now the next cell, of course, relies on having the value of x. But notice this output part of the cell did not update corresponding to what I had changed previously. And so this is where students can get into trouble, where they make a change in a cell and then don't run the corresponding cells that depend upon it, or do not rerun the corresponding cells that depend upon it. So I can rerun it, and now it updates to the correct value. So that's just a little bit of a warning that when you use a notebook interface like this, that you can get into trouble if you're not careful. Okay, so let's see. We are now on page 9. Okay, so let me start the project. Now, one of the annoying things about using CoCalc when you use it for free is that you do at the top of your screen have this information up here that says, okay, why don't you go ahead and pay for it? So if you want to pay for it, you can, but I don't think you'll need to in our class. So I have a particular Jupyter notebook. Notice the extension here, .ipynb. That's the Jupyter notebook file extension. It comes simply through some of its original origins associated with Python. And my notebook is called PDF as well. This notebook is something that I've created to correspond to the examples that we've been doing associated with the transaction time example. You can download this notebook from my website, and then I will show you later about how you can actually upload it to CoCalc so that you can interact with it. Inside this notebook, I do, again, various calculations that we've already done before, but now in using Sage. So to begin with here, if I want to do a comment in a Jupyter notebook, when I'm using Sage with it, I can use a pound sign, just like what we had with R. Now, whenever you create a variable in Sage, it's best to actually declare it first. So I can say var parentheses quote x end quote. I can do single quotes, or I can do double quotes with it. It doesn't matter. And then I'm going to then, you can actually then also put a comment at the end of the line. Then I hit enter. I type a new command to Sage. Let's assume that x is greater than 0. That's what it is for our transaction time example. And then I can simply type in my corresponding PDF, as much you would expect in terms of the syntax. And then if I say f of x again, and if I run it, I take a little bit of time. Notice the syntax here that I'm using here. I actually say f parentheses x and parentheses. That tells Sage that you do have a mathematical function that is a function of the variable x. And then Sage gives me back the actual mathematical function. Let's do some integration now. Now remember, the area underneath our curve should be equal to 1. And how do we find that? Well, we take an integral. So in Sage, the function is called integral. The first argument is what you're trying to integrate. Second argument, what are you integrating over? I'm trying to integrate over x. And then the third argument is what's my lower limit? Fourth argument, what's my upper limit? Notice the Sage terminology here. It actually uses the word infinity to represent infinity. And so if I run that code, well, I don't need to rerun it because the answer is already there. I have a 1 there. So one thing I want to point out with respect to these notebooks, sorry I didn't bring this up before. So when you save it, and then if you reopen this notebook again, all the output associated with it is saved in the notebook itself so that you don't need to rerun it. Obviously, if you make a change, though, you would need to rerun it. Okay. Also in Sage, you can do plots. So if I plot f of x from x equals 0 to 140, you get what you would expect. Unfortunately, my screen is actually, I've increased the font size of my screen, so that's why we're not necessarily seeing the whole plot. Oh, now we are. So there's the actual plot. If I want to find the probability x is greater than 30, as you might expect, I use the integral function, f of x. I'm integrating over x. I'm integrating from 30 to infinity, and I get e to the negative 1. So notice how, in comparison to r, it doesn't give us the actual numerical result. That's because it does everything symbolically first. If I want to, I could save the results from this integration to a variable called prob, for the lack of a better name. And then if I type prob again and run it, I get the e to the negative 1. Of course, at times we will want to numerically evaluate the end result. And there's a function in Sage called n to do that for us. So I want to numerically evaluate prob, and I want to do it to 4 decimal places. So I get 0.3679. Now there's a different syntax that you can also use associated with this, and you'll see this in other languages like Python, where you take the variable that you have, in this case prob, you put a dot, and then you put the corresponding function name after it to say, this is what I want to do with this particular variable name. So I say prob.n, I want to use 4 digits, and I get exactly the same result. I could also use round to round to 4 decimal places if I wanted to. Okay, let's do this other example where we wanted to find the 0.95 quantile. And again, what we're trying to do is solve for c in a particular equation, or an equation that's set equal to 0. In other words, we want to find the root of that equation. So I need to declare what c is. It's a variable. I want to assume c is greater than 0. And our equation that we're trying to find the root of, remember, is 0.95 minus the integral of f of x. I'm integrating with respect to x. I'm integrating with a lower bound of 0, upper bound of c. And so if I put that into a variable called eq for equation, then I can use the function in Sage called find underscore root. What do I want to find the root of? Well, equation, or eq. And I want to search from 0 to 300. And so Sage then does the math for you, and it gives you the right result of 89.87. So it's pretty slick. Also, in this particular notebook that I want you to take a look at now on your own, is I show how to find the CDF. I show how to use the diff function in Sage that allows us to do derivatives or differentiate. If you want to find help associated with a particular function, type the function name, question mark at the end, and then run it. Okay, so that gives you some of the basics of how to do various calculus things associated with Sage. There's a few other things I want to show you though first, before we move on. If I click on Files up here, you can see a list of all the Jupyter notebooks and other files that I've created in my free account at cocalc.com. So this gives me a convenient way to go back to something that I've done before. Now, if I want to, let's say, upload, let's say, a particular Jupyter notebook, maybe something you've downloaded from my website, if you wanted to upload it, you can use then the corresponding buttons over here to actually upload. You can also download as well. Just click on this, and then you can go ahead, and fortunately it's not showing up right now, but there is a way to then, actually I think I need to come over here, File, download, I can download my Jupyter notebook to my own computer itself. Do note that Jupyter notebooks are plain ASCII text, so you can actually open it up into a text editor and view it. But because of the syntax that is added by the Jupyter notebook, it can be a little bit harder to read. Also notice here I have a tab that has my particular Jupyter notebook open, or my particular notebook open. I can open up other tabs as well by just simply coming back to my files here and clicking on a particular notebook that I've already created for our course. Okay, so that's cocalc.com. Let's actually come back here to my notes. Also on your own, I want you to take a look at how I use it with the insurance example as well. In that particular example, our random variable x is a discrete random variable. So rather than integrating, we're going to be using sums to find corresponding probabilities. And as you might imagine, there is a sum function in Sage that allows you to do that. And here's examples of how I did that. Okay. Now there's other software packages out there for symbolic integration, symbolic algebra, symbolic differentiation as well. In the past, when I've taught this course, I've used a package called Maple. I really like it, but I decided not to use it for our course here because it is not free. It's fairly cheap for students, but for faculty and for people outside of the university environment, it can be quite expensive. So that's why I decided to use Sage instead. Another commonly used software package to do the stuff like that we would want to do with symbolic integration is one called Mathematica. And similarly to Maple, it can be expensive for non-students. One nice little thing about Mathematica is that on their website, they have a nice, not as nice of an interface as what we just saw with cocalc.com, but they do have an interface that you can use for free to do symbolic integration. And there's a simple example right there. Okay, so with that, that ends this section on doing integration with a software package. It's going to be very useful for our course. It's going to simplify your lives. So I do recommend that you take the time to do it. As I've said before, what I've found in this particular course, one of the most difficult things is for students to do the integration. But once I started using software packages to do the integration, that has helped a lot. But still, those students who want to do everything by hand, they unfortunately tend to have more errors. So even if you don't want to use a software package like this to do your integration, I do recommend that you at least try to incorporate it in some way so that you can at least check your answers. So with that then, that's the end of this particular section.